All right, let us start today. So we will continue our discussion that we started last class, which is to talk about fluids. Last time, we got a few big equations we talked about. The first one, of course, being Bernoulli. And the Bernoulli equation was a relationship very similar to conservation of energy. But instead of talking about how energy is conserved, this particular equation tells you about how the pressure is conserved in, let's say, in a pipe system or some system that's closed off. And what it says is, given a pipe system, as that's how we're going to use it. That's why I keep using the example of a pipe, water flowing through pipes. So given this system, a pipe will have water flowing through it, and the pipe will constrict or expand. It'll move up to the second floor or down to the basement. And we want to find out, how do all these changes affect the pressure or the velocity or different characteristics of the fluid which flows through the pipes? And so it says that the pressure at some location in the system, plus a term which deals with how the fluid moves, its velocity. And that term, of course, is 1/2 rho v1 squared. So rho being the density of the fluid. So that's the term, or that's the variable which tells you what fluid are we talking about. Do we have oil flowing through these pipes? Do we have water? Is this air, like an air conditioning system? What is the material? What is the fluid which is flowing? Rho, the density, is what kind of tells us what we're talking about. V, little v, that's the velocity. How fast is the fluid moving in this particular location of the system? And then the last term is the term which deals with how changing the height, moving up or moving down, will affect the pressure in these pipes or in the fluid. And that is rho times G, G being the normal 9.8 we use for gravity, times H, H being the height. And of course, this makes sense. I mean, if you have a pipe system like this versus a pipe system like this, well, if this is the starting location, there's definitely going to be more pressure trying to push the water down this way in this particular example, rather than to the right down that way in that example. So how the height of your pipe system changes will affect which way the pressure will push. Is the water naturally going to want to flow to the left, or is it going to want to flow through the right? Now, that's a big extreme example, one direction versus the other, opposite directions. But there's even smaller examples too, where if you go higher up, there's going to be a bigger change in the pressure versus if you only move up just a little bit, there'll only be a little bit of pressure difference there. Okay, so that's what this term tells you about. As you change height, the water will want to move in specific ways because gravity is trying to push the water downhill. Well, anyway, Bernoulli's equation says if you add up all of these terms, all the different terms that deal with the pressure in the fluid, it's constant. So if you look at another location in the pipe system and you look at these three terms at that second location and you add them up, it'll be the same number. So we say P2 plus 1/2 rho V2 squared plus rho GH2. Okay, so that's why I say it's kind of like conservation of energy, in that conservation of energy said you have the kinetic energy initially plus the potential energy initially equals the kinetic energy plus the potential energy final. That is to say, the total energy at one location must be the same as the total energy at another location, but maybe some of the kinetic turns into potential or the potential turns into kinetic. That's possible. Same thing here. You may have a lot of pressure in location one, and the velocity of the fluid's kind of small, but then you change the system in some way. And so over here at location two, all of a sudden the fluid's flowing faster. So the V term is bigger. And to balance, the pressure then must go down. So the different terms can change, but the total value on the left must equal the total value on the right. So that was Bernoulli. And of course, last time we related it to airplanes and how airplanes can fly, and the fact that as a fluid moves, the faster the fluid moves, the lower its pressure. And so for an airplane wing, it's designed in a very specific way as to force the air that goes over the top of the wing to move faster than below the wing. Thus, the pressure below the wing is higher than the pressure above, so you have more force pushing up, lifting the plane off the ground. Now, this wasn't the only equation, of course. We also got what's called the continuity equation. Continuity. And this equation is what allows us to figure out how does the velocity change based on the pipes. Why would the speed of the fluid change in a pipe system? You have a pump at the water station, it's pumping water to your house. It gets to your house. Well, what would make the velocity of the fluid all of a sudden speed up or slow down? It should just keep going like it normally is. And it turns out that the speed of the fluid can change based on how big the pipe is. If you change the size of the pipe that the fluid flows through, that'll change how fast the water or the fluid can move. And specifically, the equation goes like this. It says that either you could call it the volume flow rate, that's the amount of water that flows per second, or the mass flow rate, which is the mass of the water that flows per second. So you can say a gallon per second or a kilogram per second, doesn't matter. That flow rate is constant in a pipe system. So no matter where you check on a pipe, if you know the flow rate at one location, then everywhere else you check, no matter how big or small the pipe gets, it'll be the same flow rate there as well. And of course, we know that the only way for this to be true, if you have a big old huge open pipe and you have 5 gallons of water flowing per second through that part of the pipe, and then all of a sudden you constrict it down to a very, very small little pipe, well, the only way you could still get all of that 5 gallons per second to flow through the small part is if the water or the fluid that flows through the small part is now moving faster than it was in the big part. And so it says A1, which is like a measure of the size of the pipe. It's the area of the opening times the velocity of the fluid at that location. So A1 times V1, that's the volume flow rate. 1 gallon per second, let's say, must be equal to A2 times V2. Okay, so the volume flow rate at one location must be the same as the volume flow rate at another. So if you have a big pipe moving at 10 meters per second, and then all of a sudden you make the area smaller, so now it's a smaller pipe, the only way for this equation to hold true is if the V2, the second velocity, gets bigger. So that when you multiply the numbers, you get the same answer. And so with these two equations, that's what we're going to be using for this particular portion of the topic to solve some problems. All right. So let's say we do an example. So here's an example. You have a pipe which contains water. flowing with a speed of 10 meters per second. Let the radius of the beginning part of the system be 20 centimeters. Okay. Then the pipe, let's say, constricts to 10 centimeters in radius. Calculate the change in pressure. So there we go. There's our question. Now, one extra piece of information I need to give you is that the density of water, let it be 1,000 kilograms per cubic meter. Okay. All right, so this is a nice typical type of question for this particular topic. How do we want to go about solving it? Well, when I read this question, I see I have a pipe system of fluid flowing through there. There's talk about velocities. There's talk about the change in the size of the pipes. And I'm looking for something about the pressure. All of that tells me I'm going to be using Bernoulli's equation. So I write down Bernoulli's equation just to remind me what it looks like. P1 plus 1/2 rho V1 squared plus rho GH1 is P2 plus 1/2 rho V2 squared plus rho GH2. So that's the equation I'm going to want to use. Now, one thing I can do is to try to visualize what the system looks like. Okay. So if I were to visualize it, I'd say we have a pipe. It's of a certain size and it's going along. We have the water flowing through this pipe, and then it constricts down to a smaller size. Okay. And I'm told that the radius at the first part of the pipe, call it R1, is 20 centimeters. And the radius at the second part of the pipe, R2, is 10 centimeters. And what I'd like to find out is the change in the pressure. Now, what does change in pressure mean? Because my equation doesn't really say anything about a change in pressure. It has pressure 1, or it's got pressure 2. But I don't want what is pressure 2, or I don't want what is pressure 1. I want the change. And if you remember, in physics, when we talk about the difference in something or the change in something, we usually mean something like final minus initial. In this case, what I'm being asked for is the change in pressure means I want P2 minus P1. That's the change in the pressure. It was something at P1. It's now something at P2. The change is the difference in those two values. So I'm going to be solving this equation for P2 minus P1. So I'll have P2 minus P1 equals blah, 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 a whole bunch of stuff. Now, what else do I know? Well, my question doesn't tell me anything about changing heights. I'm not told I go to the second floor or I move down a hill or anything like that. So I'm assuming the pipe is just straight. It's not changing heights. And because of that, I can go ahead and just assume I don't need to worry about the height terms. They just cancel out. They're the same thing. So what are we left with? We're left with P1 plus 1/2 rho V1 squared equals P2 plus 1/2 rho V2 squared. Okay. All right, any questions so far in my analysis?
So if there's not a change in height that's listed in the problem, we can just cross out the third portion.
Yeah, and the reason you can do that, I say you cancel it out, but really what's going on is if we were to just plug in numbers, 1,000 times 9.8, and then just give it a height. Let's say we're currently at the 10-meter mark or something. And then over here on the second side, what numbers would we have? Well, still 1,000, still 9.8. And if we didn't change height, we're still at the 10-meter mark. Well, we have the same numbers on both sides. So when we move them, let's say I move the rho GH1 over to the right side, I subtract it. When they subtract, they just cancel out. And so what this tells you is anytime you have an equation like this, and there's something that doesn't change, in this case, the height didn't change. Well, if the height didn't change and it's the same fluid, then the term that has height in it just cancels out. The same would be true if the velocity doesn't change. If I know the velocity of my fluid doesn't change in this problem, then I could cancel out the velocity terms too, because they would, when you do the math, you'd subtract one from the other, and since they're the same numbers, they just go away. So yeah, anytime you're given a problem and the problem doesn't say anything about a change in height or anything like that, if you're staying at the same height, then you could just get rid of those terms because you don't need them. They're not going to change. Okay, any other questions before I move on?
I got a question. So, when they were talking about the radius,
Yeah.
So are we calculating the area at some point within this equation? Because yeah, that's my question.
Yeah, certainly it would seem that if they gave us the radius in the problem, it's probably important. But of course, if we look in our actual equation, there's nothing about radius there. So what the heck? Why do I care about the radius? Well, we're going to get to it. But yes, the fact that the radius changes, we know conceptually, because we have these other equations over here, that if the size of the pipe changes, what that tells me is the velocity changes. Because if you notice, the problem doesn't say anything about the speed changing, right? I know the original speed is 10, but I'm not told the speed changes. So why the heck didn't I cross out the velocity terms like I did the height? Well, the reason is because indirectly they tell me the speed changes, because what they say is that the size of my pipe has changed. And if I remember my intuition, if I constrict a pipe, like putting your thumb over the end of a hose, the water flows faster. And if I make the pipe bigger, the water will flow slower. So in this particular example, the problem says I'm changing the size of my pipe. In my mind, that tells me, the velocity will be changing. So let me keep the velocity here. Now, of course, what the next step is going to be is I know the first velocity, but I don't know the second. And of course, I need the second velocity to plug it into my equation. So likely I'm going to have to use the continuity equation coming up to be able to let me calculate the second velocity. And that's where the radius comes in, calculating those areas. So yeah, you're exactly right. You're kind of foreshadowing what's about to happen. Why in the world do I need the radius? Well, it's because I'm eventually going to be calculating these areas because the speed is important here. Good. Any other questions before I move on?
Yes, is this supposed to be in centimeters or meters, or it doesn't matter for this?
Yeah, very
type
good.
of equation?
Almost always, unless I specify when we're doing the theory kind of stuff, just always assume mass is in kilograms, distances, areas, volumes, all of that stuff is in meters, and time is in seconds. Those are the basic fundamental units for physics. And there are times where we kind of modify it and use other stuff, but that's rare. So here, we're given the radius in centimeters, but yes, we will be converting those things to meters eventually because we need meters for everything. Nice, good catch. Any other questions? All right, well, the next step I would do is, so I'm here with this particular equation. I've gotten rid of the height terms because they don't matter here since the height doesn't change. And I remember what I want is to calculate this P2 minus P1 thing. So let me manipulate my equation to get P2 minus P1 equals something. So how do I do that? Well, of course, P2 is already there on the right side. So let me move the P1 over to the right. And then the 1/2 rho V2 term on the right side, I want to get rid of it because I don't want that over there with the P's. I want P's by themselves and everything else on the other. So what happens? P1 gets moved to the right, it becomes negative. So it's P2 minus P1 equals, and then everything else gets moved to the left side, which means this 1/2 rho V2 squared term, I move it to the left side, he becomes negative. So I have 1/2 rho V1 squared minus 1/2 rho V2 squared. Okay, so all I did was move the terms around a little bit. I have the Bernoulli equation. I put the P's on one side and everything else on the other. And here I'm solving for P2 minus P1. There's nothing wrong with instead having solved for P1 minus P2. Why is the 2 before the 1? What, there's no reason. My assumption is maybe if I do P1 minus P2, it might come out negative, whereas P2 minus P1 would be positive. But I might be wrong too, I'm not sure. So it doesn't matter. You're either doing P2 minus P1 or you're doing P1 minus P2. The number itself is the same number. You just want the difference in these pressures. And for whatever reason in my mind, because I'm always thinking final minus initial, I put P2 minus P1. And then everything else goes on the other side. And I just have to keep track of what's positive and what's negative. I moved the 2 term over to the left, and that made him negative. And so that's why that side of the equation is 1/2 rho V1 squared minus 1/2 rho V2 squared. So that's what I want. This thing is called the change in the pressure. That's what I want. So all I need is to calculate the numbers that are on the right side. What do I need to do that? Well, 1/2 is a number, that's good. Rho, I know rho, it's 1,000. So I know what rho is. I need V1. Well, V1's given in the problem, 10 meters per second. Perfect. And V2. Well, V2 is not given in the problem. So I need to calculate them. If I could get this number, V2, then I just plug it into this equation and I'll have my answer. So now my job is calculate V2. All right, so calculate V2. How do I do that? Well, the other equation I have is a continuity equation. And that says, as you change the size of your pipe, you change the velocity. So let's use it. A1, V1 is A2, V2. And I'm trying to find this V2. Well, I need to know all the other stuff, of course. So A, what is A? That's the area. Specifically, if we're going to be technical, it's called the cross-sectional area. And what they mean by that is if you get the pipe and you cut it, what you'll have is kind of this circular hole. And so the cross section means the circle. that is the opening for this pipe. So I want the area of that circle. How do I calculate the area of a circle? It's pi r squared. So this becomes pi r1 squared, that's A1, times V1 is equal to pi r2 squared times V2. All right, so calculate for V2. How do I do that? V2 equals, I just divide over that stuff over there to the other side. So I have pi r1 squared divided by pi r2 squared. All of that times V1. Now, of course, I'm manipulating the variables here. You could have plugged the numbers in first and then manipulated the numbers. That's fine. It's the same thing. It's just I'm more comfortable manipulating the variables. So I just move the variables around. And once I've done that, now I'm going to plug my numbers in. So what do we have? Well, first the pi's cancel out because pi on top, pi on bottom, they divide each other. And so all I have is r1 squared. R1 is 20 centimeters. But centimeters is bad, as was discussed earlier. So it's 0.2 squared. And then I need R2 squared. And R2 is 10 centimeters. Again, I have to convert him. 10 centimeters is 0.1 squared. And all of that times the velocity of the fluid in the first part of my pipe, which is 10 meters per second. Oops, 10 meters per second, so 10. And so now I just plug this in my calculator. 0.2 squared divided by 0.1 squared times 10 gives me V2 must be 40 meters per second. Now, are there any questions about this? Calculating this second velocity. Can anybody tell me if looking at this answer, you could tell if it's right or wrong? Did I make a mistake here? Or do you think it's correct?
Well, based on what you said, by the pipe actually shrinking or constricting, the speed actually increased because they have to get the same amount of flow through. So it does make sense that V2 would be greater than V1.
That's perfect. Exactly right. That I couldn't have said it any better myself. Excellent. Looking at this, now I don't know if the number itself is right. Maybe I plugged something stupid in my calculator or something like that. That's always possible. However, what I can do is look at it and say, is it definitely wrong? And just as you said, in my particular example, I always have to keep in mind what the heck's going on. This is always important to keep track of when you're working a problem. Don't forget about what the problem is doing. What are we actually doing? We have a pipe and the pipe constricts. And here I'm claiming that the speed of the fluid has gone from 10 up to 40. And so I asked myself, quickly before I move on to the next step, does it make sense? Should it have gone up or should it have gone down? And just as you said, when I constrict the pipe, in order for the same amount of water to flow, the speed had to increase. Here I got 40, it used to be 10, it increased. So at least I can be confident that it seems to make sense. If when I did this, I got an answer of 4 or 5 or something like that, then I'd say, wait, something must be wrong. I had 10, now it's lower than 10, but in my mind, it should have gone up. So then I look back and I see, oh, I forgot to square something or something like that in my calculator. But perfect, exactly right. We look at the number, it seems to make sense, so I can continue. Now that I know what V2 is, I go back to my original equation, which was the change in pressure, the thing I'm looking for, is 1/2 rho V1 squared minus 1/2 rho V2 squared. And now I could plug all my numbers in because now I have all the information. 1/2 times 1,000 times V1, which is 10 squared, minus 1/2 times 1,000 times V2, which is 40 squared. And so there we go. Get my calculator, plug all of this into my calculator. So let's see. I get the change in pressure is 750,000 pascals. Or if you like, because these numbers are usually going to be kind of big, scientific notation, 7.5 times 10 to the 1, 2, 3, 4, 5 pascals. Now, technically, this is negative. So it turns out
I got a negative. That's what I was just about to say that I got a negative.
Yeah, it's a negative change. And the only reason it's a negative change is because if you remember at the beginning, I solved for P2 minus P1. If I would have said P1 minus P2, then it would have been a positive 750,000. Now, what does it mean that it's negative? What it means is the pressure in the second part of the pipe is this much lower than the original pressure. Okay, the original pressure is whatever it was. I'm not told in the problem what it was, but whatever it is, if I look and measure the pressure on the second part of the pipe, it'll be this much less than that. But okay, that's fine. If negative change in pressure is just a negative change in pressure. It's no big deal. If I would have calculated P1 minus P2 from the beginning, then I would have gotten a positive answer here. But again, it still means the same thing. What that would mean is the pressure at the beginning of the pipe is this much bigger than the pressure at the end. Okay, it's the same thing. It's just how you're thinking about it is all. But there we go. That is a nice fundamental example of a type of problem where we could use Bernoulli's equation to solve it. How did we do it? Well, again, usually what you want to do is either draw it out on a piece of paper, just sketch it, or in your mind have a vision of what it looks like. In this case, we have a pipe moving along, water's flowing through it with a certain speed, and we constrict the pipe to a smaller size. And the question is, how does the pressure change because of that constriction? Well, that type of problem, you're wanting about pressures and you're talking about fluid flowing through pipes, I always think Bernoulli. So I write down Bernoulli's equation. Here, this particular example had nothing to do with a change in height. So I just get rid of those terms. I don't need them. They're not going to affect my calculation at all. So I just cancel them out and I rewrite it. Now this is my new Bernoulli's equation. And I say, okay, I'm looking for a change in pressure. So I solve this, I manipulate this equation for P2 minus P1. I always do it that way. So now I have P2 minus P1 on one side and everything else on the other side. And then I ask myself, do I have all the numbers here to fill in to calculate the answer? If I have all the numbers, then just plug it all in. Perfect. However, here I don't have all the numbers. I'm missing something, and what I'm missing is how fast is the fluid flowing in the second part of the pipe. That's the one thing I'm not told. So I know that is the next thing I have to calculate before I can actually get my answer. So now I ask myself, how do I calculate the speed of a fluid flowing through a pipe? And I remember the only other equation I have here is the continuity equation. And that relates the velocity of a fluid to the size of the pipe. So I write down a continuity equation and I say, I'm looking for velocity 2. So I need the area of the first part of the pipe, I need the area of the second part of the pipe, and I need the original velocity. Thankfully, I'm given that stuff. I'm told the original velocity is 10. And while I'm not given the area of the pipe, I am told the radius. but that's no big deal because I know how to calculate area. It's just pi r squared because we're talking about circular pipes, nice cylinders. So perfect. I do pi r squared for area, plug in my numbers, solving for V2. Now, of course, we have to be very careful, as was brought up by someone earlier, that we have the correct units when we do this calculation, because it's very easy to miss the fact that these radii are given in centimeters rather than meters. So I make sure I convert my centimeters to meters, plug all my numbers in, and I solve for V2. I now know how fast the fluid is moving in the second part of the pipe. And before I accept it, I take the extra couple of seconds to think about it and say, does it seem okay? Or should I look back and make sure I didn't do something wrong? In this case, because I constricted my pipe, I expect the velocity to speed up. And indeed, that's what I found. So perfect. I can move on with that. Now I know the velocity in the second part of the pipe. That means I know everything I need to calculate my actual answer. So I plug all the numbers into my original Bernoulli's equation, and I get my answer.
Do you have a pre-lecture video for this? Like to look, I'm trying to find more examples I can do.
Yeah. I'm fairly confident on Canvas. There is in the module section for fluids, there's a section on that has recorded lectures from last year on this particular topic. So there's the theory video as well as an examples video. And there's also the practice problems and solutions posted as well. So that's already there. And we're going to continue doing more example problems. This, unfortunately, is only one example. It took about 30, 35 minutes to do because I was walking it fairly slowly. But we're going to do more examples. But yeah, on Canvas, not only are these particular Zoom lectures posted there, but I did also post the last year's recorded lecture as well. So if you want to take a look at that and see some other examples, you're more than welcome to.
I have a couple questions. So for Pascal's, it's the symbol is PA.
Yeah, that's
Okay,
right.
I was just making sure. And will we always need the continuity equation in order to plug in for the I don't want to say his name wrong, the other equation?
Bernoulli, right. No, you will not always use continuity equation. That particular equation is only ever useful if you have the change in the size of a pipe. Okay, so if you notice this particular example, we had a change in the size of the pipe, but there was no height difference. Well, I could also give you an example where the pipe remains the same size the whole time, but goes up to the second floor of a house. Well, for that particular example, you have to keep the terms with the heights, but you could get rid of the terms with the velocities because the speed of the fluid won't change since the size of the pipe didn't change. And if you don't worry about the speed of the fluid, then who needs the continuity equation? So the only time continuity equation is helpful or useful or needed is number one, you'll have a change in the size of the pipe. And along with that, I don't tell you both velocities. Because that's another thing I can do. I could give you both velocities from the beginning. Here, I told you the first velocity, but I didn't tell you the second because I wanted you to use continuity. However, there's nothing stopping a person from creating a question where you're just given both velocities from the beginning. And if that's the case, then you don't have to calculate it. So you don't need to use continuity. Okay. Does that make sense?
Yes.
Perfect. Any other questions?
Would you use the same process if it was the pipes were going smaller to larger?
Absolutely. It would be the exact identical process. What you will see different is when you go and calculate this speed using continuity, instead of it being 40, instead of it being bigger, it'll be a number that's less. So maybe you get, a speed of 2 or speed of 4 or something like that. But there you go. That's the new speed. Plug that speed into Bernoulli's equation and you'll have a different change in pressure. And likely, if that was the example, then what we would find for the change in pressure would be a positive number rather than negative, because you went from a little thin pipe to a big pipe. Well, I know the pressure in a big pipe is bigger than the pressure in a small pipe. So I would expect the change to be a positive change. I gained pressure by doing that. So yeah, there's nothing stop, of course, it's natural for whatever reason, when we create these problems, you go from the big pipe to the small pipe. But there's nothing stopping me from doing the exact opposite. But the process, thankfully, would be identical. Same thing, same two equations. The only difference is what number would you get as the velocity? You'll get a smaller speed rather than a bigger speed. Any other questions? All right, I hope this is making sense. Obviously, we haven't gotten a good amount of examples yet, but at least I hope it's fairly clear what the method is. It's 1:45. We only have 5 minutes. There's no way I'd be able to finish another example. So I'll go ahead and end it here. Next class, we'll do more examples. And in fact, I definitely want to do an example where we have all three terms. So I want to do an example where the size of the pipe changes and the height changes. Thankfully, it's not going to be that big of a deal. It's going to be the same process. It's just that we have an extra set of terms with the heights sitting there as well. But that'll only come into play at the very end here. You'll just know those numbers and there'll be more stuff to add. But it'll be the same process. You start with Bernoulli, move the terms around to solve for P2 minus P1, then do continuity to calculate the new velocity, then plug all your numbers in at the very end of the day to solve for your delta P. Okay, so that's the plan. Next class, more examples on this, just to make sure we're understanding it. And then probably Monday of next week, we'll move on to the second part of fluids, which will be Archimedes. What else? Oh, I will be posting a little homework problem for you to try yourself. I'll probably post it tonight. And as always, I'll give till next week to work on it. So you'll have time to do it. But I definitely want to post something to give you something to try. Make sure you try it yourself, see how you're doing. And just to add more stuff to, for grades, to make sure that, I always hated as a student when the grades were made based on a very small amount of things, because if you mess up on just one of them, it's a big deal. But if we have a whole bunch of different assignments, then if you messed up on one, it's not a big deal. It doesn't affect you all that much. So I will be posting the homework, but of course I'll send an email to let you know when it's posted, and it'll be on this, the Bernoulli and continuity thing. So other than that, if you have no questions, you're free to go for the day, and I will see you on Friday.
Have a good day.
All right. Thank you. You too.